Hello, Mr. Sorrentino here again, doing this video on 6.6 determinants in Cramer's rule. And I mentioned determinants here and there in the previous lesson because that was one thing that helped us would determine whether or not a matrix had an inverse or not. Being able to calculate the determinant becomes something that's necessary for that, but it's also something that alone can be used to find the solution to a system of equations using Cramer's rule. So the very first thing you learn how to do is the determinant of a 2 by 2 matrix, because a 2 by 2 matrix is a very simple process of figuring out, its determinant. And essentially, if I'm given a matrix as shown here, then all I need to do basically is carry through the multiplication and difference. I would multiply in this direction first, and then this direction second, and subtract the two results. So it's kind of like a cross multiplication type of thing we have going on here. So for instance, if we want to do that for example 1 here, where I'm asked to find a determinant of -8, 6, -1, 2. And notice, when you're asked to find a determinant, they're going to use like absolute value marks instead of typical matrix brackets for that, so don't get alarmed if you see that. That's just the shortcut of writing find the determinant of that matrix. And as you can see, that's notation's used up here as well. So as mentioned up there, to find the determinant, I just got to do this first. I'm going to have, that's going to equal -8 times 2. I'll write it out more than needed. Minus, and then the second one I do in this direction, -1 times 6. And so that ends up being -16 minus a -6, which means I'd be adding subtracting a negative is the same thing as adding. So -16 plus 6 would give me a -10. So this determinant could be used for some calculations we'll show a little bit later in Cramer's rule, but this would also let me know that, the matrix, -8, 6, -1, 2 would have some sort of inverse, because this determinant does not equal 0. So that's something that could be used for that. Now, the procedure, if you have a 3 by 3 or above matrix, is a little bit more involved, because we really only have this formula type situation for 2 by 2 matrices. So how do we handle a 3 by 3 matrix or bigger? Let's take a moment now and see how that goes. So you can see here, and some of this wording here got cut off from the notes. So you have them in your notes, but I'll go to that when I get to it. The procedure of finding the determinant of a bigger dimensioned matrix is a little bit more involved. What I have to do first is choose a row of the matrix. So for the case in point, for my situation here, I'm going to choose this top row here. Now sometimes they'll tell you to expand across a certain row. Make sure that you follow that, because especially in like the My Math Lab homework, they tell you to expand across a certain row. That's going to affect some of the intermediate answers you have to do when you fill in your information. So I'm choosing row 1 in this case. The step 2, write the equation using symbolic notation of elements of A and cofactors of A. So we have this new thing called cofactor. So what is a cofactor? Well, a cofactor is basically involves you finding the minor as well, because if you see here, let me pull this over a little bit. So this comes from your notes. The cofactor is basically some power of -1, where I and j are the row and column numbers for a particular element, and I add those together and raise it. That's going to be my -1 power, and then I'm going to do a minor of ij. Now, the minor should be a smaller matrix that hopefully it gets to be a 2 by 2. You can do this procedure. If the minor ends up being a 3 by 3 matrix, then you have to like break that down further into 2 by 2 matrices, and we don't usually have you go quite that far, because that would be a very long and painful process. Because the minor of a matrix is just the determinant of a matrix that eliminates row I and column j. That's the important part here. Whenever I say M of ij, that's a matrix determinant of a matrix that eliminates row I and column j of a given matrix A. So what does that mean here? So let's have a look and see what we're trying to do with this. So when I expand this matrix equation, I gotta try to scooch this over again. If I expand across the first row, that means that the determinant of A is going to equal, it's going to equal this element here times, theoretically, I would say A of 1, 1 plus this one here, negative 4 times A of 1, 2 plus this one here, negative 6 times A of 1, 3. Now each one of those gets expanded a bit further, and that's what step 3 is going to ask you to do. So we're just writing it with these cofactors in mind, but now we have to actually work out what these cofactors are in terms of their minors. So when I go down to the next step, step 3, I'm still going to have my 7. A of 1, 1 means I'm going to multiply this to negative 1 to the 1 plus 1 power. Now, I'm going to write it all out here, but you should be able to do 1 plus 1 in your head and just say that's 2. Times the minor of 1, 1. So let me do some erasing up here. Still want to show that I'm expanding across this row here. When I do the minor of 1, 1, I'm essentially saying, okay, I'm going to take the matrix that results after I get rid of this column in this row. So the minor matrix, or the minor determinant, would be, in this case, 0, negative 3, 2, negative 5. And you see, that's a determinant I could find using the formula we used from example 1. And I would do the same thing for the next one. I would say, okay, plus negative 4 times negative 1 raised to the 1 plus 2 power times, now coming back up here again, since I'm looking at element negative 4, I would be eliminating the first row again, but now this column. And so the matrix, the determinant matrix I'm left with there is I'm going to have 2, negative 1, negative 3, negative 5. And then for the last one, I'm going to have plus negative 6 times negative 1 to the 1 plus 3 power, again, row number, column number, times, coming back up here again, still eliminating the first row because I'm going where the negative 6 is, but now I'm going to eliminate the last column, and the minor matrix that's left over after that is 2, 0, negative 1, 2. So that's my formula expressed with cofactors expressed as operations with minors. And this is where I need to get to. Now I could do the computation. So let me scooch this up a little bit. I'm going to calculate the value. So when I work this out now, I'm going to have the determinant of A equaling 7 times negative 1 squared is just 1. 1 plus 1 is 2, so negative 1 squared. Times, now the determinant, again, I'm going to do that crisscross pattern. I'm going to have 0 minus negative 6 is going to give me 6. Negative 4 times 4 times negative 1 to the 1 plus 2 is 3, so that's going to be times negative 1. 2 times negative 5 is negative 10 minus positive 3, so negative 10 minus 3 is a negative 13. Plus negative 6. 1 plus 3 is to the 4th power, So negative 1 to the fourth power is going to be a positive 1 times 2 times 2 is 4 minus negative 1 times 0, which is 0, so I'm going to have 4. So simplifying even further, I'm going to have 42 minus 52 minus 24, and that's going to equal a negative 34. So the determinant of A equals a negative 34. And you're shown on your notes, and I have it written down here again. Show you how to do it on your calculator. And a 3 by 3 matrix is pretty much going to be the highest order matrix that you're responsible for being able to find using this method. You may be given some problems that are in your textbook that has a higher one, and it's good practice to do it. And they do show you a procedure for it, but we're not going to get too far into doing that, and you're not going to certainly be given any problems where you have to find the determinant of a 4 by 4 matrix without using a calculator. So you can still expand by minors if you want to use this process on a 4 by 4 matrix, as we're going to talk about Cramer's rule momentarily. You certainly can, except you could go through and make it a little easier, just finding the determinant of the matrix in question. So for example 3, you're being asked to find the determinant of a matrix on your own by expanding across the third row. So let me pull that one up. Okay, so we're being told to expand across the third row. So I'm going to expand across this row right here. So, and I'm going to write out some of the steps. I'm not going to go as hog wild with them before. The determinant of B is going to equal 1 times the B of 3, 1 plus 2 times B of 3, 2 plus negative 1 times B of 3, 3. And so that's going to be 1 times negative 1. 3 and 1 is fourth power. And I already know what the minor matrix is going to be, because I can kind of imagine I'm just going to eliminate this column, for 1. So I'm going to have my minor matrix right here. The determinant of negative 6, 7, 1, 3 plus 2 times negative 1 to the fifth power, 3 and 2. And now when I look to eliminate my matrix, so I'm still expanding across this row. Now I'm just going to be eliminating this column. So the matrix I'm going to have to determine of there is going to be negative 4, 2, 7, 3. Got a little hog wild with writing that as long as I did. And lastly, plus negative 1 times another negative 1. This negative 1 is coming from the formula for a cofactor of the sixth power. That's 3 and 3. And the determinant, again, still expanding across the bottom row. So I'm still eliminating that row, but I'm now eliminating this column. And so I'm going to have negative 4, negative 6, 2, and 1. So I have all these 2 by 2, and that got bigger as I moved to the right. That's kind of weird. So as I do this, I want to find these determinants. So negative 1 to the fourth is 1, so I'm just going to have a 1 times this determinant. Negative 6 times 3 is negative 18, minus 7 is going to be a negative 25, plus negative 1 to the fifth is negative 1, times 2 is negative 2. So I'm going to have negative 2 times negative 4 times 3 is negative 12, minus 14 is going to give me a negative 26. And I'm going to have negative 1 times negative 1 to the 6. Negative 1 to the 6 is going to be just 1, so I'm going to have just the negative 1 here times that determinant. Negative 4 times 1 is negative 4, minus a negative 12, which is 2 times negative 6. So negative 4 minus a negative 12 is going to give me a positive 8. So here I'm going to have negative 25 plus 52 minus 8, and that gives me a determinant of 19. So that's a procedure for finding the determinants by hand. That's as far as it's going to go for you being able to do that. I mean, you're not going to be expected to find the determinant by hand for anything that uses, 4x4s and things like that. Not that you won't be asked to maybe use the rules that we're about to go over for a 4x4 situation, but you would certainly be able to use the calculator to find the determinant in those instances for sure. So, which gets us into Cramer's rule. So let's have a look at what Cramer's rule is saying. And Cramer's rule is basically giving us a method of using determinants to figure out what the solutions to a system of equations is. It's actually a very time-saving process. It's not as fast as doing A inverse times B, but it is more of probably the faster algebraic method. Because again, finding determinants, even if you're doing them by hand, is not super difficult. It's just knowing the procedure and remembering what you're doing at any time. So if you're given a 2x2 matrix, they're saying that x equals the determinant sub x over the determinant d, and y equals the determinant sub y. And basically what these two mean, if you look here, d is just the regular determinant of the matrix. So you're finding the determinant of your coefficients. dx is me taking this coefficient matrix, replacing the x column with the result column. So the c's are being put over where the a's were, or my x column was. Remember, this is my x column. Typically, this is my y column. And I'm replacing the x column with, the right-hand side. And in dy, I'm doing the similar thing, so now I'm replacing the y column with the right-hand side. And if I find these determinants, and then do these ratios that are being defined up here, then I would be able to find a solution to the system of equations. And much like that, for a 3x3 matrix, well, let's do a 2x2 one first. So, excuse me. If I want to set up these matrices, these determinants, D is just going to be the determinant of my coefficient matrix. So the 3, the -4, the 2, and the 3 would be here. D sub x is going to be the right-hand side values, replacing the x column and keeping the y column. And dy is going to be me keeping the x column from my regular determinant and replacing the y column with what's on the right-hand side of the equal signs. So these are the three determinants I need to find in order for me to figure out what the final answer is. It's a 2x2 situation, so you don't have to worry about cofactors and minors. That's just going to be 3 times 3 minus -4 times 2, or 9 minus a -8, so that's going to be +8, that's going to be 17. dx, this one here. Okay, much like the previous one, I'm going to have -7 times 3 minus 1 times -4. So I'm going to have a -21 plus 4, which gives me a -17. And lastly, d sub y. Well, same procedure. I'm going to do the 3 times 1 minus 2 times -7. So I'm going to have 3. 2 times -7 is -14, so minus a -14 is +14. And I get 17. So now, using the notes you have from Cramer's rule, which were given to you, by the formula it's dx over d, so that's going to be -17 over 17, which is -1. And y is going to be d sub y, D, which is 17 over 17, which is just 1. So the solution to this is 1, 1. And if you went through and used elimination, substitution, any other matrix methods we've done so far, you would get the exact same answer. That's negative 1, 1. So, it kind of works a little easier than doing row operations. I would certainly say this is a heck of a lot easier than a row operation. Not quite as easy as just saying, okay, find the inverse on your calculator for the left-hand side. But if you were doing this all by hand, I would say this would be the way to go. Because, and certainly on a final, if you're asked to do it, and you have especially a 3x3 situation, Cramer's rule might be the way to go for just, for the sake of speed. So Cramer's rule, very similar. Now I'm going to have a dx, dy, and dz, or whatever the letters we're using for the variables, as well as d. And it's still the same premise. Dx, here's the determinant d. I'm just taking the coefficient matrix on this side. All the coefficients. Dx is me replacing the right-hand side for the x column. The dy is me replacing the right-hand side for the y column. And the dz is me replacing the right-hand side within the z column. Again, I have to work under the premise that the determinant's not equal to 0. Because if the determinant did equal to 0, I would have a special case. If you get a determinant of 0, that means you're not going to be able to use Cramer's rule because it doesn't have a determinant. You're not going to be able to find an inverse and use the inverse matrix method. And you're going to have a special case. Each one of those special cases means that if you would do row operations, that way, you would get a row of zeros when you're eventually doing all those row operations, which means you wouldn't be able to complete it. Then it just takes a little bit of time to consider if it's a situation where you have infinite solutions or no solution, and that could take a little bit of time with a 3x3 matrix. We usually don't give you too many instances of no solutions or infinite solutions and with 3 equations and 3 unknowns, only because of the fact that it's a little harder to tell than if you're doing 2 equations and 2 unknowns. We talked about methods for that, and it's usually easy to tell quite easily in the process of doing your elimination or substitution if that's the case with that. So let's have a look at a 3x3 situation here. Now that you're showing some calculator steps here, and I'm just going to kind of demonstrate it. I'm going to kind of show this because, I could go through and certainly set up the matrix and everything. And certainly, you should do it as well. But, and I could go through all the row operations and whatnot, but for the sake of time in this video, I do want to show how the calculator can be used to do this. But first, what I need to do is I have to realize there's a little trickiness to this one here. This last row here, right here, I'm missing my y term. So I have to realize that my coefficient matrix, A, is going to be 2, 1, 3, negative 3, 1, 0, negative 1, 1, 2. And so if I'm doing D, that's going to be, of course, this is the determinant of this matrix. Dx is going to be the determinant of replacing the 2, 1, 3 column with the right-hand side, so 4, 3, 11, and the rest of the matrix being left alone. Dy, I'm going to have the 2, 1, 3 here. It's going to be the middle column that's replacing the 4, 3, 11 is going to replace the middle column. And of course, dz is going to be the 2, 1, 3, the negative 3, 1, and 0 in this column. And of course, the last column gets replaced with the 4, 3, and 11. And I would find those determinants. So to demonstrate that, I'm going to show you how to do it on the calculator. Now, with the calculator, what the steps you're showing your notes are doing is kind of showing you how to go through and find the determinants, how to set up you would set up 4 different matrices to do this. Um, I don't really have to do it that way. I'm just kind of showing that there. I'm going to show a different method here, only because now if you look at if you look at what's given in your notes and as well as what you're looking in this video, you'll have a couple different methods to do it. So I'm just going to take care of these matrices one at a time. So I'm going to take this matrix here, and I'm just going to let this go into A. So I'm just going to hit second in matrix. I'm going to go to Edit, Matrix A, and I'm going to make that a 3 by 3. And I'm just going to put the numbers in. It's best to hit the Enter button because it'll just take you right through it, and change to the right area. I find it works nicer that way. Now the method I'm showing here is making you have to retype things. I'm going to eventually edit this at some point. Get a little carried away there. Go to Enter. But it can save you some recopying, methods, but you're doing a lot of saving and putting things into matrices that, you don't really have to do. So I have matrix A here, although it's going to be matrix D in this. And I want to find the determinant of this. So if I just go to second matrix, I'm going to do math. I want to do a determinant. Oh, I have to be careful. One thing you have to be careful about, and I'm glad this happened because I forgot. You can actually have matrices made up of matrices, where an element of a matrix is actually another matrix. And I can also have a situation where an element of a matrix could be a determinant of another matrix. Now, we're not getting into that kind of linear algebra here. So let's clear this out of here. Just say that's 2 again. So you want to make sure before you start trying to do any calculations, you want to make sure you get out of this edit menu before you do anything. So now what I could do is second matrix, find my determinant, and then say second matrix again, and do matrix A. And so I get the determinant of matrix A to be 4. So I'll just write that here. It's going to disappear for a second. Now if I'm going to do dx, dy, and dz. So, and I'm just going to change the one matrix I have. So cover up this one here. So so I'm going to go back to second matrix, go over to edit again, go to my 3 by 3 matrix, and now the only thing that's going to be different with this one is that I'm going to change this column to be 4. I'm hitting the down arrow now to save me myself a little time. 4, 3, and 11. And now I'm just going to go back, quit, and if I just hit enter again, it's going to, the last command was do determinant of A. So I do it here, it's going to also be 4. So I know this is 4. Bringing those back up again. Going back to my matrix. So there's shortcuts you can do with this, depending on which method you choose to use. Now when I alter this matrix, now I have 2 columns to fix. So I have to put this one back into 2, 1, and 3. This one here, I have to make it back to, then I have to change this to the 4, the 3, and the 11. And now I have my dy set up. Hit enter again here. I'm going to get -8, so that's what this one is. And of course, the last one, dz. Change my matrix again. When I go to edit, remember, when you're choosing names, that means you're putting a matrix into some sort of calculation. So this is going to be back to the -3. I must have hit some. -3, 1, and 0. And here I'm going to hit the 4, the 3, and the 11. And so if I do determinant of A again, I'm going to get 16. So now I have all these things. I have D, I have dx, I have dy, I have dz. We know x equals dx over d, which in this case is 4 over 4, so that equals 1. We know that y equals dy over d, and that equals negative 8 over 4, which is negative 2. And we know that z equals dz over d, and that's 16 over 4, which is 4. So my solution to this is 1, negative 2, 4. And that's how you do it. So, as I said, this calculator method down here is kind of showing you how you put it into many different matrices and come up with the values. And that is section 6.7, Systems of Linear Inequalities and Linear Programming. So a lot of the information we're going to be seeing here is certainly a lot simpler than the things we had been covering in Chapter 6 prior to this. The only time we're going to have to use some information that we used in prior parts of this chapter is when we started looking at systems of inequalities and we have to know any specific points from them, which is what we do in linear programming. As far as though, graphing linear inequalities and solving systems of inequalities, you're not going to basically, just have like one set answer, even if you say I'm going to solve a system of inequalities. What you're going to be looking for is a region on the graph that basically has ordered pairs that would satisfy the conditions of both, all 3, 4, all 4, whatever, how many inequalities you got. So, but before we can start getting into doing multiple inequalities, let's see what we do for single inequalities and how we would go about graphing them. So, and I'm going to give myself some space on both sides here. When I have a linear inequality, which basically means I'm just going to have an inequality symbol where I normally have the equal sign. But as far as what I do to solve this, or what I do to graph it, I still like to put it in slope-intercept form for 2 reasons. 1, it makes it easier to graph in the long run, and 2, it lets me know where to shade along with that. So here's what I mean. Let's first put this into a slope-intercept form, which means we want to solve this inequality for y. So if I wanted to go through and do that, I would subtract 2x from both sides, and then I would divide both sides by 3, making sure on that right hand side I am distributing. And so I would end up with y is greater than or equal to negative 2/3 x plus 2. And so I would simply start graphing this the same way I would normally graph any line. So I would start up 2 on the y-axis, and I'd find additional points by going down 2 and right 3. Of course, I could also go up 2 and left 3, just to get some more points. Especially if you don't have a ruler, which I'm going to make use of one here to make it look nice and neat. Now, before I start drawing a line with this, I do have greater than or equal to. So that's important because the equal to part means that things along this line satisfy the equation. So like, for instance, the point 0, 2 is on this line. If I put 0, 2 in, 0 for x and 2 for y, I would get 6. Is 6 greater than or equal to 6? Well, yes, it is. It meets the equal to part. So things along the line are included, which means I'm going to draw this as a normal solid line, as I normally would. And because I have this in the slope-intercept form, the fact I have a greater than means I should shade above the line. Ordered pair in that region would make this inequality true. More than likely producing things that are greater than 6. We do the same thing for b. I'm going to solve this one for y, so I'm going to subtract x from both sides. So I have negative 4y is greater than negative x plus 8. Now I'm going to divide by negative 4, When I divide by a negative in an inequality, I do have to switch around the inequality sign. There's actually a 1 here before, so I'm going to have -1 divided by -4, which is 1/4 x. And 8 divided by -4 is a -2. Again, I have to distribute that division. That's why it's important, just because I had a greater than or equal to sign or a greater than sign in the original inequality, if it's not in the slope-intercept form, it's hard for me to determine if I should be shading above or below without, putting some points in and seeing how it works. And it's certainly a way you could deal with it. I mean, this is certainly more of a shortcut. What I'm going to do is I'm going to graph this line again. So I'm going to go down -2 on the y-axis and go up 1, right 4, up 1, right 4, up 1, right 4. I can also do down 1 and left 4 as well. Now, when I do this, anything along the line 1/4 x minus 2 is not going to make this true. Like, for instance, like the 0, -2, it's on the line. But if I put those points in 0 and 2, 0 and -2 for this, I would have 8 being greater than 8. That's not a true statement. So basically, anything along the line is going to make the left-hand side equal 8. Being equal to 8 is not what I'm looking for here. So that means that in this case here, this boundary line that I'm drawing is not included. So when I draw it, I do have to draw it dashed, which ends up it's the boundary, but it's not, anything on the boundary is not considered part of the answer. So when I draw this, I'm going to draw it dashed. So there's my dashed line. And then that it's in this form, I can now say, okay, well, I'm going to now let it shade below the line because it's less than. Another way of doing that, if you're unsure, if you did it right, is just pick a point that's clearly in one area or the other. I mean, if it's available, I choose the origin because zeros are easy to work with. And if I put 0, 0 in for the x and y, does it make it true? If the answer is yes, then whatever region the origin's in is going to be the solution area. If it doesn't work, it's not going to be. So the other region would be the solution. But generally, if you put it in slope-intercept form, the greater than or less than portion of your inequality will tell you above or below. So that's how you go about graphing linear inequalities. Now next, we're going to look at graphing systems of linear inequalities, which basically we're doing this procedure a couple times and we're looking for overlap. So let's have a look at that. So for part A of number 2, I have two inequalities. I have x is greater than or equal to -2, and I have y is greater than or equal to 3 minus 2x. The first one's not too hard to do because, I mean, if I had x equals -2, it's a vertical line. That means all my x's are -2's. So x equals -2 would be here. It's harder to do the above and below, but remember when I'm dealing with x's here, it's a solid line again because I have the equal to part. Being greater than -2 means I'm in this region over to the right. So I'm just going to shade that part here. Now I'm going to look at the second one. The second one, I can rearrange it just a little bit. It's already solved for y. Looks more like slope-intercept form if I have it in this format. So I know when I graph it, I'm going to start up 3 and go down 2, right 1, or up 2, left 1. And I would shade above that, but I'm not going to really shade what's already been shaded before. So the feasible region or the answer to this is going to be this region right here. I'm sorry if it seemed like it was doing a lot of jumping around there, but it was having some issues with the computer. So, but that region right there is where I would have solutions to this inequality. Let's try the next one. To graph these, and again, this is an instance here where for some reason my the axes aren't showing up quite as well as I'd like to see them, so I'm going to put them in really quick. So, and I'm going to start with the two easy ones. I'm going to start with x is greater than or equal to 1. So here's where 1 is. It's a solid line because I do have the equal to part. And I would be shading to the right hand side. I'm not going to do a whole lot of shading because it's going to get really mixed as I go through it, but this right hand side is where I'm shading for that one here. So I took care of this one. For y is greater than or equal to 2, I'd have a horizontal line there, so I'm going to put that in. Again, it's going to be a solid line. And for that, I would be shading above. So we're looking at this region now here. Now I'm going to go to the top equation. I'm going to put that in terms of y. So I'm going to have 2y is less than or equal to negative x plus 10. Divide both sides by 2. I get y is less than or equal to negative 1/2 x plus 5. So it has a y-intercept of 5, and I'm going to move down 1 and right 2. So put some points in here, and I'm going to graph it now. Again, a solid line because it was the equal to parts in there. And you can see a lot of the linear programming problems, it's going to be the case. But for this region, since I do have the less than sign, and sorry if there's any jumping around going on here. There was some issues with the recording before. It's now going to be this region in here. I mean, because it's below the green line. And lastly, and now I'm going to figure out this one in terms of y. So y is going to be less than or equal to negative 2x plus 10. So I'm going to plot some points. And I'm going to graph the line. And now I would be shading below that line. So the overall feasible region now, I'm just going to graph this in a nice dark color, is this region right here. So in that little region in there, and I'll even zoom in on it a little bit, is going to make up every ordered pair that makes all 4 of these inequalities true at the same time. And this is a lot of what we're going to be doing when we're dealing with linear programming. In linear programming, we're going to get these inequalities from descriptions in the problem. We're going to find this feasible region. It might be the case we might have to eventually find like these intersection points. Now some of them will be kind of easier to find because we know the specific x value already and we know which equations it's going through. Other ones, like maybe this one right here, it might be a little harder to find because I had to find this, solve that system of equations to find out what that intersection point is, but that kind of goes back to the work we've done prior to this. So let's take a look at some linear programming problem and the process needed to do that. So the process of linear programming involves these steps here. You're going to read the problem because you're going to be given a word problem in all these cases. And you want to translate the information into a system of inequalities. These inequalities will be known as the constraints. The way you know these are going to be things that are, the constraints, because there's going to be another thing we're going to be looking for, which is an equation that will be known as the objective function. The objective function is typically, going to center around whatever you're trying to either maximize or minimize. And that's what most of these problems are going to be like. You're going to be maximizing or minimizing something, whether it's cost, profit, weight, whatever. The constraints are going to be limitations. You have to have so much of this. You have to have at least some of this. When you see those words involving specific things in the problem, those are going to define your constraints. So you're going to take the inequalities and graph the feasible region, and you're going to need to find the coordinates of the vertices of that feasible region. So that's where solving systems of equations might come into play. And then lastly, you're going to use those vertex points in the objective function to see which one provides the minimum or maximum that you're looking for. So let's have a look at this example down here on minimizing cost, and we'll see how to go about doing this. I'm going to zoom out just a tad. So an animal feed is to be made from soybean meal and alfalfa. The mix must contain at least 120 pounds of protein, 24 pounds of fat, and 10 pounds of mineral ash. So it's these levels of protein, fat, and mineral ash that's going to be defining our constraints. Now, each one of these provides some of those, so that's where the rest of the inequality is going to come from. Each 100-pound sack of soybean meal costs $15 and contains 50 pounds of protein, 8 pounds of fat, and 5 pounds of mineral ash. Each 100-pound sack of alfalfa costs $8 and contains 10 pounds of protein, 6 pounds of fat, and 8 pounds of mineral ash. How many sacks of each should be used to minimize the cost? We want to see if there's a happy medium. So if I buy a combination of the two, would I be able to possibly minimize my costs as much? And that's what I'm looking to do, is minimize the cost. So when I start dissecting this problem, what I'm looking for is how many sacks of each. So that's going to be my variables. So I'm going to let X be the number of sacks. 100 pounds has nothing to do with anything here because the sacks themselves are 100 pounds. So, but I want the number of sacks of soybean meal. And I'll let Y equal the number of sacks of alfalfa. And that's very important. Our objective function, I always find it's best to figure out what that is first. I want this objective function in terms of X and Y. It's going to be cost. We want to minimize the cost, so the cost is going to be, well, each X is $15, so $15 times X would tell me how much that would cost for the soybean meal. 8 times Y would tell me how much I'd be spending on the alfalfa, and adding them together would give me the total cost. So that's my objective function. That's what I will use later. What I want to have now are my constraints. What we come up with, our combination has to have certain levels of protein, fat, and mineral ash. I'll just do some abbreviation of that. Those are going to be defined constraints. Those are the ones that are defined outright, but there's also the fact that, I'm going to use the fact that I know that X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. It's basically just saying that I can't have negative sacks of these items because that wouldn't make any sense with respect to this problem. And that's why, and that's already taken care of by the fact that we're only graphing in region 1, where I have positive X and Y's. So that's why it's set up this way. So these have already been kind of taken care of, but it's always important to kind of keep those in mind because some things are going to be implied. You should know that they have to be positive depending on the circumstance or what have you. So I need to come up with 3 formulas for this. Since the soybean meal gives me 50 pounds of protein per sack, and the alfalfa gives me 20 pounds per sack. If I add those together, I should get the 120 pounds I need. That has to be greater than or equal to, because I need at least 120 pounds. If I have more, that's cool. That's why it says at least. For the fat, I have to have at least 24 pounds of fat. 8 of that does come from the soybean meal. 6 pounds comes from the alfalfa. And lastly, the mineral ash, I need to have at least 10 pounds of mineral ash. Each sack of the soybean meal will give me 5. Each sack of the alfalfa will give me 8. So these are my constraints that I'm going to graph and find a feasible region for. So with these constraints, I'm going to graph my feasible region. I'm going to do this in fast motion here and then kind of sum everything up when I get there. So there generally is my graphs and my feasible region. I made them a different color so I can keep track of them. I didn't show all the calculations I did to graph the lines, but when I put them in slope-intercept form, the red line goes, it has a y-intercept at 6, and it has a slope of -5/2. So I made sure I had that. The second one, the fat line, which I did in purple, has a y-intercept of 4 and has a slope of -4/3. And then the mineral ash one, a little bit more problematic because it has a lot of fractions involved. You put it in slope-intercept form, but it does have, it's easy to determine it has an x-intercept at 2, because 5 times 2 is 10, and plus the y would be 0. And then I just have to figure out what the slope is and use this, and the slope was basically a negative 5/8. So, so that's what those lines are showing. Now, as you see here, the feasible region, because it's all greater than or equal to, and of course the axes are also included as well. So it has to be above. It has to be above the x-axis, to the right of the y-axis, and above each of these lines. If you see here, the mineral ash line doesn't really play much of a role in this. It's going to be the protein, the fat that really determine, how many of each to buy, because it just seems as though like the mineral ash will be satisfied if I get the protein and fat mixtures down enough at this point. So what I need to do now is determine the vertices for these. And some of them are really easy because some of them were part of the graphing process. So like this vertex here, now it only has vertices at one end. It's not a feasible region that's been cut off, and you're going to see that a lot with situation where you have to minimize stuff. Is that you're going to see it's a pretty open feasible region and it only has boundaries on like one side of it. So 0, 6 is one set. So basically that's saying, okay, that's buying all alfalfa, no soybean meal. This one down here is at 3, 0. And that would be the instance of me having all soybean meal and no alfalfa. But you notice it's only 3 sacks of that as compared to buying 6 sacks of that other stuff that's cheaper. There's also one other vertex here, and that's the intersection between these two, the protein and fat lines. And so what you need to do here is you would need to solve the system of equations 50x plus 20y is equal to 120, and 8x plus 6y is equal to 24. You have to solve that system to get that intercept. Just for the sake of argument, I'm not going to go through a process here because
you know several ways of solving a system of equations.
Using your own method. The answers should be essentially in fraction form 12 sevenths, 12 sevenths. If you didn't get that as a solution, go back and look over your method, try to find any errors you may have made along the way, and if you can't, try another method to see if you can get closer to the right answer so you know which method works best for you. So now I have my 3 vertices. There's no more vertices. These are the 3 I'm going to try out. So I'm going to now go back to my objective function right here, and I'm going to use that and come up with, okay, I have x's, y's, and cost. So I can either have none of those, 6 of those, 12 sevenths of those, and 12 sevenths of those, or 3 of those and none of those. And I put each one of these into that cost function. So 15 times 0 plus 8 times 6 is going to give me a cost of $48. That one's pretty easy to do, and so's the 3, 0 one. 15 times 3 is 45 plus 8 times 0, which is 0. It's going to be $45. So if I was just comparing, buying all of one versus the other, it'd be cheaper to buy all of the soybean meal because I only need 3 sacks of that and get all the nutrients needed, as compared to having to buy 6 sacks if I only buy alfalfa. Well, let's see if I buy a mixture of them, in this case basically 12 sevenths, which is 1 5/7 of a sack of each, will that give me a smaller cost? So if I do that, put 15 times 12 sevenths and 8 times 12 sevenths and add them together, I get approximately $39.43. So I'm just putting into this function right here. So that's the cheaper one to go with. Now it might be harder to buy them in realistic terms, but you might be able to say, okay, well say this is like a week's supply. You could buy 7 weeks at a time, which means you'd basically buy 12 sacks of each, And then you would mix it up and split it into, weekly rations to give to, whatever, your animal feed. So, but generally, to minimize costs, 1 5/7 sacks of each feed would meet the conditions and minimize cost. And that is the end of this example, and that is the end of this video. So if you have any further questions on this process, please make sure to see me during office hours or ask about it during class time. And until I see you then, and since there will be no more videos, this is the last one, I'll see you around and have a good day. And hopefully by this point, you know where you are in the course, and hopefully you enjoyed this course overall throughout, or learned a lot from it, or both. So I'll see you around. Have a good day.